Okay, welcome back to part 5 of this short course on Radiance Fields. This is also the last lecture of this short lecture series. And this lecture is going to be a little bit of a medley of different topics. So it's not like, last 4 lectures where we had like one thing that we were focusing on. Today we're going to be focusing on a few different things. Some of you suggested some topics on Monday. So although I can't cover everything, I'm going to try my best to cover some of the more important ones. Okay. All right. So let's do a recap of what we've seen so far. We started off by looking at the history of how, as humans, we've been recording shape and appearance of the world, right? So starting right from biological vision all the way to, things that we've developed as humans for recording stuff, starting with photography, analog, film, all the way now to radiance fields where we are capturing reality as closely as we can, capturing the shape and appearance of reality. Then we talked about radiance fields. Radiance fields have a very specific meaning in physics, and we borrow a lot from physics, right? We talked about the light field, the planoptic function, and how the radiance field is, how the relationship between the radiance field and light field, right? So we talked about those things. And then we talked about neural radiance fields, which is a method to capture radiance fields using a neural network, which was introduced in 2010. And then there was a lot of excitement about that, and there was a lot of interest that a lot of researchers started working on this problem after that. Then we talked about 3D Gaussian splatting, which is a relatively speaking new way to capture the radiance field using 3D Gaussian functions that are attached to things in 3D space, right? And these Gaussian functions have properties that they contain, things like color, mean, variance, opacity, right? So they have these properties. Right? And what the problem of fitting a radiance field essentially boils down to optimizing for the best set of parameters for these 3D Gaussian functions that produce the best results. Okay. In the previous lecture, part 4, we talked about applications of radiance fields, and specifically we saw 2 applications: capturing human motion. So we talked about grasping, right? And how 3D Gaussian splatting, we can build an articulating model of articulated 3D Gaussian splatting model that can capture how humans move our fingers, how we articulate our fingers, and how we can use that to understand things like contact. When we try to grasp an object, we make contact, and we can capture this without using any markers, just using cameras, right? So we can capture that. So we talked about that. And then we also talked a little bit about a dynamic scene. So if you have scenes where things are moving, how do we capture that using radiance fields, right? So we talked about data sets and so on. So this last lecture is, as I said, going to be a mixture of different things. Most of this work is at the bleeding edge. These are topics that researchers are actively working on. I'll be talking a little bit about hardware, a little bit about priors. Maybe I'll show 1 or 2 examples of robotics. And I'll end with some outlook of commercial applications as well. So maybe some of you are interested in starting companies, and radiance fields are already being deployed widely in many of these things, right? And we'll see some examples of how this is being commercialized. Okay, any questions before we begin? All right, okay, let's dive straight into this. So the first thing that we're going to talk about is priors. I mean, one of the questions that keeps coming up during the course of this lecture series is, oh, we need 50 cameras, we need 100 cameras, right? So that seems like it's a lot of images that we need in order to be able to produce these things, right? What if we could get away with using fewer cameras, right? What if we had only 1 image? Can we use that 1 image to build a radiance field, right? So that's a question that naturally comes up. And there's obviously been a lot of work. Again, this is not a literature review. I'm not going to cover everything. I'm just going to take one example that I'm most familiar with because I was a co-author on this one. And I'm going to talk about how we do that here, right? And by definition, I mean, from a pure signal processing perspective, if you assume that the radiance field is your signal, you need to have sufficient samples in order to be able to reconstruct that signal, okay? If you have only a single image, when you have lots of images, that gives you sufficient samples in order to capture the underlying signal, which is the radiance field, right? So that's what we do when we have lots of camera views. However, in many cases, we might have just 1 image, right? And we might want to produce a radiance field from this 1 image. But if you have a situation like this, you have to hallucinate. Like you have to use prior knowledge to fill in the gaps. Because, let's say you have a picture of a chair, you don't know how the chair looks like from the background. but you've probably seen many chairs before, right? So even though you don't know the exact shape and appearance of this chair in the parts that you don't see, you've probably seen chairs like this before. So you can reason based on this prior knowledge, right? So that's what we mean when we say using priors, right? And this is often referred to as generalization. So you've seen a lot of examples, and you want to be able to reason based on the examples that you've seen before. Okay? And this was work that was led by Bipasha, Gaurav, and Aditya, who were all, back when we did the work, students at IIIT Hyderabad. They're all, at least Bipasha and Aditya are now at MIT. Okay. All right. So we wanted to study this problem of single view radiance field reconstruction. So let's say you have an image that looks like this, has a lot of objects, it has a chair that you like, and you'd like to create a 3D model of this chair represented as a radiance field. Okay, so that's what you'd like to do. So what the method that we built, which we call HipNerf, and it'll become obvious why we call it that, essentially takes this input image, does some kind of stuff we'll talk about, uses something known as a hypernetwork, we'll talk about that in a moment, and it produces a radiance field reconstruction that you see on the right over there, right? So the chair that you see there is based on the chair that we've observed in the images, in this image, sorry, and we're creating a 3D version represented as a radiance field. In this case, this is a neural radiance field. So what you see on the right is a neural radiance field. Okay, so that's the problem setting. Now we wanted to go one more step further, right? So what we wanted to do was, what if you didn't have any image, but you just had a text description? Let's say the text description was, I'd like to have a 3D model of an avocado chair, right? What do you do, right? I think that's something that comes up often as well. And this is very similar to generative AI, right? So you can go to ChatGPT, ask it to produce an image. You could describe the image, it gives you an image, right? So it's the same setting here. We have some kind of a text description, and we're going to ask it to synthesize the neural radiance field corresponding to that. So here again, we do some stuff, which we will talk about in a moment, use something known as a hypernetwork, and we get something that looks like this, right? So a chair that is roughly shaped like an avocado, and it's green in color, right? So that's kind of what you get. Okay, so we call this approach HipNerf because we use something known as hypernetworks. And how many of you are familiar with hypernetworks? Okay, not a lot. So let's take a quick overview of what hypernetworks are. It's very easy. Okay, so let's say you have a neural network. I mean, this neural network is similar. It's a fully connected neural network. In this case, it's an MLP, right? And this neural network could represent anything. For example, it could capture the radiance field like we have in a neural radiance field, okay, NERF. So that's what we have. The neural network, if you fix the architecture of the neural network, so that's the number of layers and the number of neurons that you have, once you fix the architecture, you can uniquely determine different versions of this neural network through the weights of this neural network, okay? So that's what, when you train this neural network on lots of data, what you're really changing are, the knobs that you're tuning are essentially the weights of the neural network, okay? So let's represent those weights by, so this whole neural network is represented by f of x, so it's a function, and theta represents the weights of the neural network here, okay? So this is what we know already from machine learning. Now, what a hypernetwork does is a hypernetwork is another network. Let's call this network Z, the input to this network Z. So we'll talk about that in a moment. And let's call this network G of Z, okay? Now, instead of trying to learn a neural radiance field or some other property of the world directly from data, what this hypernetwork does is it learns the weights of this main network, okay? So it takes as input some input Z, and it outputs theta directly. So what you can do is you can simply take the output of this hypernetwork, set this as the weights of your primary network, your main network, and that hopefully learns something, right? So this is what we call a hypernetwork, right? So when we learn theta and set that as weights for my main network, what we have is known as a hypernetwork architecture. Does it make sense? So it's kind of like this is often referred to as meta learning, right? Because you have this network that's doing this meta task. It's actually not solving your task directly, but it's actually predicting the weights of a network that's going to solve your task, right? So that's what we call a hypernetwork. And oftentimes people refer to this as meta learning, learning to learn, right? So these are all terms that you might have heard before.
What is ZESM?
Yeah, so we'll usually this can simply be just some random noise, right? So that is something that people do, or it can be, we'll talk about that in a moment, it can be some conditioning input, right? So let's say you want this, let's say this is a nerve, right? So this is a neural radiance field. You want it to look like an avocado chair, right? So you would give that an encoding of your text description, avocado chair, as Z here, right? And then this hypernetwork will predict the weights that will produce an avocado chair. So it can be that. Or it could be an image. So let's say you have a single view image, and then you want to predict a nerve that looks like what you would see. Okay. All right. Does it make sense? Any questions about hypernetworks?
So basically, the theta should be the number of parameters.
The theta is the number of parameters. So it's actually a pretty large output space, right? So if you have like a million weights here, you'd have a million outputs here. Yeah. All right. Yeah, so here's some references in case you'd like to take a look. Hypernetworks don't seem to be super popular these days, but a couple of years ago, they were, there was lots of excitement about how we could use them. All right. So HipNerve is the work that the method that we built, right? And as the name suggests, HipNerve is a hypernetwork version of nerve, okay? So what it does is, forget about the codebook. So let's say here, instead of the codebook, we had some kind of an input image. So that could be a single image of an object that we're trying to reconstruct, or it could be a text description of the object that we want, right? So that's what we have here. And then what HipNerve does, HipNerve is actually a hypernetwork. It's a combination of a hypernetwork and a nerve, right? So we have two networks, right? So that's inside this, this is just the hypernetwork. HipNerve is just the hypernetwork. And HipNerve predicts the weights of a nerve neural network, okay? So that's what we have here on the right. And for the sake of this discussion, let's ignore what's on the left. So that's a very, very simple architecture, right? So we just have a hypernetwork that predicts the weights of my nerve network, right? And once we have the nerve, we can then just do volumetric rendering, right? So you can create rays in at certain positions, directions, sample points along the ray, do ray marching, accumulate everything, and then we get the integrated radiance, right? That's it. So the architecture is really, really straightforward. It's just two multi-layer perceptrons, right? And they're not even that big, right? So the hypernetwork, I think, has fewer parameters than the primary network, right? So that's the architecture that we have. Now, the trick here is we're going to learn this on lots of data. So we're going to take existing data sets. For example, there is a data set called ShapeNet, which has lots of chairs, lots of tables, lots of cars, airplanes, etc. Right? These are 3D models of different categories of shapes. So what we do is we take this data set, render, let's say you have 1,000 different chairs, right? You would render all of these chairs, you would render virtual views of all of these chairs, use that to build a neural radiance field, okay? Then you would have this, you would train your hypernetwork so that it predicts, based on that supervision that you have, the right set of weights so that you get chairs that look like what you trained it on. Right? So it's a fully supervised approach. You have training data where you have 3D models of chairs, you render lots of images, you build a nerve. Once you have the nerve, you then train your hypernetwork to predict the parameters of this nerve that gives you the best rendering result after you do the volume rendering. Okay? So it's a very, very, very straightforward architecture. There's no complicated function here. It's just two neural networks. Okay, questions? Any questions about this?
For one object, you require one hypernetwork?
No, the hypernetwork is shared across everything. Right? So essentially, good question. So what happens to this hypernetwork is it learns priors across all different chair shapes, all different table shapes, all different airplane shapes, right? So the way you train this on thousands of chairs. You don't train it on one chair, right? So the hypernetworks learns to generalize. So that if you give some input, Zn, so it could either be some random noise, or it could be some encoded version of your image or your text description, this hypernetwork spits out weights, which then look like a chair.
So my question was, will the same hyperparameter will be used for, hypernetwork will be used for chair and table as well?
Yeah, so there's different versions we tried this on. You can do both, right? Better performance, you train this within a category, right? So if you need the best performance, you do category-specific training. If you have more capacity, then you can do across-category training. Yeah.
The losses on the MLP weights as well as the rendered images?
Yeah, again, I think it's been a while, but I think there's been we tried a couple of variants, one on the MLP weights, but we also tried one directly, the rendering loss at the end, right? So no loss on the weights at all, right? And even that worked well, right? So you don't actually need to have loss on the weights themselves, right? So even if the weights are off a little bit, it doesn't really matter because you have so many weights, right? So just the final loss is just on the rendering loss.
So in a way, the hypernetwork gives initialization for this MLP-based objects.
It gives the final weights actually. So we don't retrain the nerve.
So nothing is learned in the second one.
Yeah, absolutely nothing. Yeah, it's just a dummy architecture, and then you just plug in the weights into this dummy architecture, right? And that instantly transforms into a nerve that makes sense when you do the rendering.
So during training, these weights are assigned, and these weights are taken as a output for the training of hypno.
No, so there's two processes: training and inference. During training, we have lots of chairs. Okay, so that's the input. So we train this hyper network so that the weights that it outputs create chairs that look like our training data. Okay, so that's the training process. We do this on thousands of chairs.
For training, we need the labeled data also for hypno. What is that labeled data?
Yeah, so for training, we have lots of chairs and we have rendered images of chairs.
But the output of that hypno is weights notion, which we don't
Correct.
know on beforehand before training.
Yeah, so as I said, we trained two variants of this, right? So in the first variant, we actually, for every chair, we fit a nerve. So if you have 1,000 chairs, we fit 1,000 nerves. Then we take the weights. Then you can supervise it, right? So that's version number one. Version number two is you don't do that at all, right? You just directly ask it to predict something and then try your rendering loss after that. Right? Okay. All right, so that's the hip nerve architecture. Oh yeah, question.
Since this is working on only one image, won't the generated nerve have like issues of what are word coordinates compared to the?
Yeah, so good question. The dataset that we use, ShapeNet, actually specifically we use something known as the ShapeNet core dataset, where they've manually oriented all chairs to face in the same direction. So coordinate system doesn't turn out to be a problem because the 3D models that we have all the chairs facing in the same way. So this is known as canonicalization, this process. Okay, all right. So there's a bunch of details in here. Maybe I shouldn't go too much into the details here, but essentially, this is the architecture of the hypernetwork. And if you look carefully, it doesn't even have so many layers, right? So it just has a bunch of fully connected layers, and that's basically it. So it's a pretty straightforward, simple MLP that we use, right? And the same thing applies also to the neural radiance field, which is also a bunch of fully connected layers. Okay? So it's a pretty reasonable architecture. Okay, let's look at some results. These are all on real images, by the way, right? So although we trained this on CAD models, we can test it on real images because CAD models, especially for things like chairs, are pretty close to what we see in reality, right? All right, so on the left, you have a real image. It's just a single image. You're going to take only a part of that image that contains a couch, right? This is how, we also do some segmentation. We remove the background so that it doesn't interfere with the reconstructions. And then this is what we get, right? So we don't see anything about the rear part of the chair, right? Or rear part of this couch, right? We don't know anything about that. But what we get is a reconstruction that looks like this, right? Obviously, it misses the pillows here, right? Because the training data does not have pillows. But the chair that we get, or the couch that we get, is similar to the couch that we're observing. So it's a two-seater. It has like 4 elevated legs, right? So you get all of that stuff as well, right? And you get appearance, reasonably good appearance of the chair, the couch as well, right? So this is what HipNerve does. Here's a couple of more examples. Again, these are in the wild examples. So these are examples that we've seen in natural images. And this is a pretty challenging example because this chair is, you don't see a lot of this chair, right? So you only see one cross section of it, and the method is able to reconstruct the dimples of the chair and the cushion, right? So things like that as well. Because I guess cushion chairs need to have dimples, and maybe this is reflected in the data. And this is where the prior knowledge comes into the picture, right? Although we see so little of the chair, it's using this knowledge that we gained from looking at thousands and thousands of chairs and use it to essentially fill in the blanks, right? Or hallucinate, right? So that's really what's going on here. Okay. Another thing that you can do is this hypernetwork. You can either give it some encoded version of your image, or you can give it some encoded text description. Right? So the example of this avocado chair that we talked about earlier, right? So if you have an avocado chair, you can take that text description, avocado chair, use your favorite language encoder, BERT, clip, whatever, right? Take that encoded input, pass it through your hypernetwork. Of course, you'd have to train this as well, right? So in order to train this, you need shape text pairs, right? And ShapeNet has this, right? So we can train this on ShapeNet in a similar fashion. And this is what you get, right? So a sleek wooden chair with white legs. So this is what you get, right? And this is again using the same hypernetwork architecture, right? A peach circular chair, so you get something that looks like this. A wooden chair with a white seat, right? So you get something that looks like. Okay, so that's again one example of how you would use priors, incorporate priors, even though you have very sparse description, so just a single image or just one sentence or one phrase that describes what you want, and you're able to synthesize a 3D NERF model based on that, right? So that's how you would hallucinate and use prior information to do this hallucination in a reasonable way. All right, so that's just one example. Again, this is a couple of years old. There's been a lot of subsequent work that improves on overall quality, overall results. So there's a lot of work that has gone into this problem space. Yeah.
How long did it take for training?
Yeah, good question. I don't know the answer to that off the top of my head. I don't think it was exorbitant because this was training across categories mostly, right? So I think we're talking about like a couple of days. But again, this work was done in 22, so GPUs were different. So if we were to do it today, it'd probably be a little bit faster. But I think it's in the order of like 3 or 4 days, I want to say.
For one category.
For one category.
So can you repeat what is the process of generating enough from text input?
Yeah, okay, let's look at this slide. So as I said, the hypernetwork has some input and it has some output, right? So the output is the weights of the nerve, right? So that's clear. It also has a way to provide input, right? So usually, if you give it some random input, so just like we do with diffusion models, you create some kind of random noise and provide that as input. Same thing here, right? You can do that, and you'll get some output, but there's no guarantee that the output looks like what you want, right? So we can then replace this noise with some encoded version of things we care about. So this can either be images. So if this were an image, you would take an image, run it through some kind of a VGG encoder, take that feature, right, flatten it, and provide that as input, right? Or if it's a text description, then you would use BERT or CLIP or any such model, and then you would provide the encoded version of that text description as the input to this hypernetwork. Yeah?
How do you align the modality as the input? You couldn't understand text out of the box or images aligned.
We don't do any alignment. So we just take some encoded version of images in text, and we let the hypernetwork figure it out. Right? So there is no explicit alignment, pixel level alignment, none of that.
Okay, and you mentioned that it's fully supervised. So are there paired text images?
Yes. So we have paired. So we have CAD models that also have text descriptions, right? So we have text CAD model pairs, and if you have a CAD model, you can render using computer graphics techniques. You can render how things look like. Okay. All right. So as I said, there's been a significant amount of progress that's been made since. I just wanted to take like one very, very recent example, which is how can you use generative video models, right, in order to fill in the gaps? Because again, one limitation of Radiance field reconstruction is that we need lots of different views, right? We might not always have all these different views. Now, what if you had maybe not one, because if you have one, the amount of prior knowledge that you need to use is extreme, right? Especially when cases where everything is mostly self-occluded, right? But let's say you had like 5 views, right? Can you build a radiance field from that? It seems like you should be able to, right? Yet, if you take any common 3D GS or NERF method with 5 views, it's not going to work very well. You're not going to get very good reconstructions, right? So this is a recent paper that uses video diffusion models. So models that are capable of synthesizing videos to fill in the gaps, essentially, right? And what they do is something pretty straight. Actually, before we do that, is everybody familiar with video diffusion models? Has everybody seen them? Yeah. Okay.
Just little, if you can just.
Sure. Yeah. Okay. All right. I don't have detailed slides, but I will show you this nice, cool video, which is from Google's VO2 video generator. So what you're seeing here is a car drifting in some kind of a big city, right? Every single pixel in this video was synthesized. This is not real. Okay. So none of the pixels here are real. Everything was generated. Right? And this is generated using this very large video diffusion model that Google has created. It's known as VO2. I don't think it's available for public consumption yet. But it's probably trained on, because Google has access to YouTube. They probably trained it on all of YouTube, right? And you can synthesize pixels like this, right? So this is a very, very large model. Probably took several $1 million to create, right? So it's a very expensive affair, very expensive, time-consuming affair. Okay. Now the question is, if you look at this video again, you see everything looks realistic, right? It looks like the world is 3D, the camera is spanning, the car is moving, right? So there's a lot of realism in this video, right? So the question we can ask is, if I don't have 100 cameras in this space, let's say I only had 5 cameras, can I create virtual cameras using a diffusion model such as this, right? And then use those virtual views to do my reconstruction, right? Create like 100 views and then do my reconstruction, right? So that's the high level idea, right? And that's kind of, that's not exactly what this paper does. They still do something else, but that's roughly what this paper tried, right? So they had 2 views of this conference room, right? So one view that looks like this, another view that looks like this. Very little overlap, right? You could still say that it's the same room because the tables look similar, the chairs look similar, right? Now, can we ask a video diffusion model to synthesize views in between and then use that to do our reconstruction, right? So that's the idea behind this paper. I'm not going to go to the details here, but essentially they do exactly that. They have a video model, it synthesizes new views, and they can do reconstruction based on that, right? They're still not doing radiance field reconstruction. They're doing a point cloud reconstruction, but you could adopt a similar idea to do radiance field reconstruction as well. And I don't remember what video model they use, but this work is from Google, so it's natural to conclude that they probably use one of their large video models. All right, so this was just, again, there's probably hundreds of papers that try to use prior knowledge, incorporate that for generalizable radiance field reconstruction. I'm just trying to sample like two of the ones that I've seen recently, right? All right, okay. Any questions so far? Okay.
What are we talking about? Pose model here, sir? Pose model.
Yeah, you can kind of ignore that. What they mean by a pose model here is some kind of a 3D reconstruction techniques that reconstructs camera pose as well as kind of like structure for motion, right? So it's not super important what this is, right? You can think of this as structure for motion. I think that's the easiest. Yeah.
Has anyone done the reverse wherein you use 3D reconstruction to have consistent frame to frame for video generation?
Yeah, it's a great question. I think there's been some effort in trying to enforce multi-view consistency within video diffusion models. But this is usually challenging because you don't have data in that direction, right? So you have a lot of video data on the internet, right? You can just use the whole thing to train your model, right? But you don't have a lot of 3D data, right? So there's no way in which you can propagate information the other way around, right? So you're fundamentally limited by data in that case. Yeah.
Was this fine-tuned or was there some training involved?
For the video model,
In this method?
the video model is locked, so it's frozen. So there's no.
Training process involved in the entire pipeline.
Yeah. I must confess, I haven't read the paper very carefully, right? So I can check that for you offline. Maybe it seems like a relevant paper, so maybe we should take a look at it also. All right. Okay, so now we're going to switch gears a little bit because one of the topics that came up in the previous lectures was how do you build cameras that can capture images of dynamic scenes, of 3D scenes, right? How do you create reconstructions of dynamic environments such as this person playing drums, right? So this is actually a radiance field reconstruction, so you can actually see the whole thing in 3D, right? So it's both the shape as well as the appearance of the world. How do you do this, right? So I'm going to talk about a project in our group, which we call Brown Interaction Capture System, BRICS for short, which is really about building the hardware that you can use to capture immersive radiance fields of scenes, right? So that's the goal for BRICS, right? And as the name indicates, we want to go beyond motion capture and we want to capture like interactions, things like how people are making contact, people are grasping and manipulating objects, and so on. So BRICS really refers to a collection of capture systems that we've built at Brown over the last few years of varying needs or varying use cases and varying sizes. Okay, the one that I talked about last time, this 1 meter cubed box, right, which we use to capture grasping and manipulation, that's the one that you see here. We call this BRICS Mini, right? So that's here's an illustration of this. It's about the size of a person. That's why we have this figure of a person here. So it's about 6 feet tall. And you can put your hands inside, you can put toys inside, and it'll capture data from 50 different cameras, right? So that's the setting that this was designed for. We've kind of built on top of this. We now have systems that are room scale. So we have entire rooms that have hundreds of cameras. So you can kind of go in there, capture very rich dynamic data, and then use radiance field based reconstruction to analyze what's happening in that scene. I mentioned this briefly last time, right? So we also have what we call BRICS Baby, which is like a cradle version of BRICS, 32 cameras to observe infant motor development skills. And we've also had plans to build like wearable versions of multiple cameras in the past so that we can capture more egocentric data where you're trying to manipulate objects, and we'd like to capture all of that in fine detail, right? Now, building these kinds of camera systems is actually not trivial. Because you think of each of this camera as a webcam that you have, right? Sure, right? Like it seems like a trivial problem. Get like 100 webcams, connect them all together, right? And you have a multi-camera capture system, right? It should be as simple as that. But there are multiple problems, and I will highlight 2 such problems first, right? The first problem is bandwidth. Any camera that you connect to your computer produces a lot of data. Video data is a lot of data. Okay? Even if you compress it, it's still a lot of data, right? And most cameras connect using USB, right? And USB has very limited bandwidth, right? So if you're using USB 2.0, it's like 480 megabits per second, right? So that's actually not a lot. You can easily saturate it with a webcam, right? And the limitation is actually on hardware. So if you have a big machine, even if you have a really big machine, you can't connect anything more than like 3 or 4 cameras to it simultaneously because you will instantly saturate the PCI Express bandwidth and you'll no longer be able to transfer all the data from the cameras, right? So what you then need is you need lots of computers, and then the computers have to talk to each other, right? So that's the big problem. Right? So how do we build systems or networks of cameras and efficiently gather all of this data and put them and store them is a big challenge, right? And there's no easy solution to it. So that's the first challenge. The second challenge is if you have a dynamic scene, you need to capture images at exactly the same time, right? This is known as temporal synchronization, okay? If one camera captures it as at one particular time, another camera captures it 50 milliseconds later, everything moves in the world fast, especially if it's like human motion. I'm waving I'm making gestures, right? These are fast motions, right? And it's very easy to miss these kinds of motions and not be able to reconstruct these kinds of motions. So that's the second issue. Even if you had so many cameras, even if you were able to gather all of this data, because you cannot connect all of these cameras to a single computer with a single clock, right? You need multiple clocks essentially. Then the clocks will all have to be synchronized, right? That's the other issue. So, for example, if you see the clock over there, it says 6:12, and then it's like 57 seconds, right? Whereas the clock on my watch is completely different. It's 6:11, and then it's like 45 seconds, right? So getting clocks synchronized is actually a pretty big challenge when we talk about computers, right? So that's the second issue. Okay, so let's leave those issues aside and let's talk about how we address this in the bricks capture system. So bricks really refers to a collection of cameras that when I talk about room scale systems that have hundreds of cameras or small systems that have 50 cameras, what we're really talking about are hundreds of high frame rate RGB cameras. You can think of these as high quality webcams, right? So that's the best way to think about these cameras, right? We also have other sensors like microphone arrays. We can also put things like accelerometers, IMUs, and so on and so forth. But primarily, we're focusing on cameras. Now, we've actually, in my group, we actually build the hardware as well, right? So it's not just all the methods that we built once we capture the data. So we built what we call smart bricks, which are essentially GoPro-sized cameras. So there's 2 cameras, gives us stereo vision, also a way to reconstruct things in metric units. So these cameras have essentially computers inside that can capture data coming from 2 USB devices, right? So they can capture this high bandwidth data. Now this version that you see here on the left is a wired version. So you have to plug in like a Ethernet cable that supplies both power as well as data transfer, right? And we get something like a gigabyte of data every second from these kinds of cameras, right? So it's a lot of data. We've also recently built like wireless versions of the same camera. I think it looks cuter, so kind of like 2 eyeballs. And this is completely wireless. So it has a battery that lasts for a couple of days. So you can capture like 2 days worth of data, and you can transfer all of this data wirelessly through Wi-Fi. Right? So you just have to connect to the Wi-Fi network, and it captures and sends all of this data. Now, the most important feature is that we designed these hardware systems to be temporally synchronized. So the idea is that we are going to put multiple of these bricks, smart bricks, in an environment where we want to capture data. And then we have hardware and algorithms that temporally synchronize the clocks across all of these different bricks. Right? So that's the interesting bit. And we can actually get it to within a few microseconds, which means that you can capture very fast motions. Right? So if you have high frame rate cameras, you can actually capture very, very high or very high speed motion with this kind of camera. Now, just for comparison, if you go buy GoPros, GoPros have this synchronization feature. And the best that they can do is something like 50 milliseconds, right? So in terms of temporal alignment, right? And that's not enough, often not enough for fast motions, sports motions, and things like that. Okay, actually, clocks are very, very fascinating. I wish I had like an entire hour where I could just talk about clock synchronization, right? But I'll give you the TLDR, right? Well, it turns out that measuring time is a tremendously difficult task, right? And the way computers do it is also, there's so much variation and so much, interesting things that happen, right? I'll actually go from the bottom, okay? So the best way to keep time is to use an atomic clock. So the atomic clock is actually some kind of a radioactive device, actually, where you look at how much a certain substance emits radiation. There's usually a pattern to it, a very strict pattern that is followed, and you can use this to keep track of time. Atomic clocks are often accurate to like a nanosecond over thousands of years, some ridiculous amount of accuracy, right? So if you have some kind of a starting point, an atomic clock can keep time very, very accurately, right? And we have standards for that. So for example, the International Atomic Time, TAI, that has its own kind of standard, and there's an atomic clock that runs all of this, right? But then it turns out that the way the Earth revolves around the sun changes, and we, as people who want to do our daily lives, we use clocks mostly to run our daily lives. We want to see the sun exactly on top of us at 12 noon, right? But that doesn't always happen because there is drift. The Earth doesn't rotate at exactly the same speed, and so on and so forth. There's lots of things that happen there. So every year, the Earth rotates slightly differently, and that introduces changes because the sun isn't going to be at exactly overhead at 12 noon. Right? So they actually correct for that, right? So most of if you look at your computer, the computer synchronizes with something known as UTC, which is Universal Coordinated Time, right? So this UTC clock keeps track of the drift of how much the Earth rotates around the sun, rotation of the Earth, compensates for all of that, and they add leap seconds. So exactly like how we have like leap year and so on, there's also leap seconds, right? So this ensures that the sun is always overhead at 12 noon, right? But real time is different from that time, right? So we have to take all of this into account when we take these pictures, right? So all of this is important, but because when you have lots of cameras, and then you have leap seconds, right? Your timestamps are not aligned exactly, right? So you could, this gets messed up quickly. Okay. And again, I'm happy to talk about this offline if you're interested, but time is keeping time is really, really fascinating. All right, so we've seen this video before. This is the capture system that we use. This is the Bricks Mini capture system. It's about a meter cube, and we can capture lots of high quality grasping manipulation data using something like this. Okay, and then I think we looked at this one as well. So this is the entire room that has 100 cameras, and we can create reconstructions of entire human body interacting with the environment using this kind of a setup. Okay, so here's an example of a mobile version of this brick system. So what we did here was, this was a kind of like a demo day where we took a random conference room and then we transformed this into a capture volume, right? So what we did was, on the walls you see our smart bricks, right? So these GoPro-sized cameras. And we put a lot of those cameras in this room. In fact, here we put something like 70 bricks in this room. And once we do that, we can create reconstructions like this, right? So this is a Radiance Field reconstruction. So you could see how we can create like immersive 3D versions of this space. There is no other sensor, right? It's all just images taken using those cameras that you see here. And you see a little bit of artifacts that look like Gaussians, right? So this is all 3D Gaussian splatting that's happening here. All right. Okay, so yeah, that's the very brief overview of the hardware systems that you need to create these kinds of multi-view 3D, 4D data. Any questions about the hardware? Yeah.
So you said that you can't have one computer taking in all of that data at once.
Correct. Yeah.
You have multiple of them.
We have multiple. Yeah.
And then you just synchronize all of them.
Correct. Yeah. Okay, so what else can you do if you had data like this, right? If you had multi-view dynamic data, what else can you do? Again, I'll show a quick example of recent work. We call this GigaHands. It's a data set work where we tried to capture a very large scale data set of human hands manipulating objects, right? So that was what we tried to do. I'll first play the teaser video. So using that capture system that I talked about, we can get data that looks like this, right? So two hands kind of interacting with each other. You can create 3D reconstructions of that. Here we are using mesh. This is not a radiance field, right? But you could do radiance fields as well. And we're capturing like fine scale interactions. So having eating a fry, cooking, different kinds of everyday interactions that you might do, right? So, and we've collected a lot of such interactions. So I think we have something like 1,400 minutes of data, right? So this is probably the largest data set for hand-hand and hand-object, bimanual hand-hand and hand-object interactions. Okay, yeah, so I'll skip through some of the details. So this is actually a hard problem. Many people have tried to do this in the past, right, using different kinds of setups. We opted for this lab setting where we have lots of cameras, so you don't have much occlusions, and you can capture all of these interactions in high detail. I'll highlight some of the interesting findings. So let me skip to that part. So there's a lot of engineering that went into this, right? So you have the raw data that kind of looks like this, right? And you have to extract things like articulation of the fingers, reconstruct the object, how do the fingers interact with the object, right? So you have to go through a lot of this stuff in order to be able to build a data set like this. And all credit goes to my PhD student, Rafu, who did this work. Okay, so let me go to the interesting bit here, which is, yeah, this one. So you can, similar to what we talked about in the previous lecture with Manus, right? You can figure out where fingers are making contact with objects, right? Now that we have a large scale data set, we can do this over the entire data set. So we can kind of draw conclusions from the entire data set. So what this figure shows is, so what you have here, this is the left hand and this is the right hand over all participants, and we had about 50 participants, right? And this heat map shows what parts of our hand we use most often to touch things, right? So for the left hand, you can see that the brightest spots are the thumb, index finger, and the middle finger, right? And then for the right hand, it seems like the fingertips are more evenly distributed because most of our participants were right-handed, right? So you can see things like that from the data as well. And funnily enough, you can also see that we sometimes use the back of our hand to move things around, right? So you can see that reflected in this data as well, right? So I thought this was all super interesting. Okay, once we have this data set, we can then train generative models from this, right? So here's an example of text-driven motion synthesis. So similar to HipNerf, where you could provide a text description and you would get a nerf model out of that, right? So here we are providing a text description. So the description is fasten the lid of the sugar canister back on, right? And the model that we built can replicate how that motion looks like, right? So it can create the hand articulations, hand motion that looks like what is being described in the text here, right? And we can do this because the entire data set that we built has this kind of annotation, right? So it has text descriptions, it has hand motion, and so on and so forth. So you can use all of that information to build something that looks like this. You can also go the other way around. This is known as motion captioning, right? So let's say you observe a person doing some kind of action or an activity. What are they doing, right? So this kind of activity recognition thing you can do here as well, right? So here, in this example, the person opens the cap of a pen, and this is what is being generated by the model, right? So it doesn't look at the image, it looks at the reconstruction of the hands that we get from the video. And once we have that, the model comes up with this kind of description, right? So again, this is the reverse problem, right? So we're not synthesizing motions from text, but given motions, we're trying to recognize what activity is being performed, right? So this is known as motion captioning.
Sir, if it is only seeing the hand motion, how is it able to identify Type-C cause of it?
Yeah, so it turns out that hand motion actually gives you clues about what object you're trying to open. I mean, if I do this, right, like, what do you think I'm holding? Exactly, right? So, it gives you clues, even if I'm not actually holding the bottle, it gives you clues about what I'm interacting with, right? And we see that from this kind of a training, right? So we don't actually use the object at all during the training. It's just the hand motions that we use.
And it is able to identify the type of cable it is with Type-C.
Yeah, and again, you have to keep in mind that this is a generative model, so it's probably hallucinating, right? Based on the data that it's observed, it's saying something. It may or may not be correct, right? But it probably looks plausible, right? That's the idea here. But in this case, I think it was right because this is a headphone cable, right? Okay, yeah, question.
The text is generated from the video, right?
From the video, we get this, right? So the text is generated from this, right?
The question is that in data set was the laptop or the setup was used.
This is all on the test set. So this was not used during training. So this is a held
I
out
think
bit,
that
right?
the laptop or similar setup, let's say.
It's possible, yeah. So it's probably seen other laptops, other people manipulating other laptops.
It might be biased toward that.
Yes, but then the data set scale is also quite big. So we call this gigahands because we have 1 billion unique views of the hand, right? So that the data set is now like billion scale. Right?
You are specifically mentioning that laptop, let's say, is a type or something. What if I take a wooden thing and then I just do this? Then it will always predict this one.
Yeah, if you mime actions, then it's probably going to say that. I mean, if I do something like this, like what would you say? I'm typing, right? But there's no keyboard here, right? So it doesn't really look at the object, right? It's only looking at how you move your fingers, right? And it's basing this analysis on how you move your fingers, right? And I think that there's probably a lot of clues in how you move your fingers that you don't actually need to know what the object is. You can actually recognize what the object is based on how fingers move.
Isn't that the Type-C power that is specific towards? Seems like it's biased towards something.
Yeah, so this is again, this is exactly like ChatGPT, right? So if you ask ChatGPT for something, right, it'll probably give you something very specific, right? But that doesn't mean that is reality. So it's a generative model that way. It's sampling from this distribution that it's learned. So if we were to resample this, right, you'd probably instead of Type C, you might get Type A, right? You don't know, right? But it's such a generative model. Okay. All right, so that's again, if you have hardware systems like this, you can do this kind of analysis. You can also do this with Radiance Fields, right? That's something that we are currently working on. Okay, somebody asked me, what about robotics, right? So how are Radiance Fields used in robotics? And again, there's a lot of work. I'm taking this very recent biased sample that I encountered, right? So this is work that uses Radiance Fields for robot teleoperation. So what is teleoperation? You want to be able to control a robot without actually being physically present with the robot, right? So you're somewhere remote, so you could either be in the next room or you could be somewhere in another country, right? And you want to control that robot, right? So that's known as teleoperation. And what this group of researchers did was they demonstrated that you could actually build Radiance Fields in real time, almost real time at a few frames per second, right? It's a low quality version of Radiance Field. It's not like super high quality that you would expect for visualization purposes. But nonetheless, if you have something that looks like this, you can use this for teleoperation. You can make it look like you are in the same space as the robot, right? And because you're able to realistically render the surroundings, that gives you an immersive feeling. And you can, the idea is that you can use this to more precisely control the robot and its actions in that particular environment, right? So, we are starting to see more and more Radiance Fields being used in robotics, a little bit for manipulation. This particular example is for teleoperation, right? And I think as Radiance Fields get faster and faster to train and fit, then I think these applications are going to become even more predominant, and you'll see them more often. All right, so in the last few minutes, what I want to do is move away from research a little bit, right, and look at perhaps commercial industrial applications of this technology, right? So here is, it seems like Radiance Fields is a somewhat new technology, right? It was reproposed in 2020, and that's where all this excitement came in. But it's already being used, especially in things like the movie industry and for making ads, right? There's many ads that have been made that use NeRF and 3D Gaussian splatting technology. I just wanted to give you like a small sample. So here's one example of, actually I forgot to add the citation. I will add the citation, but let me play this. This also has audio, so hopefully that works.
I need your attention. Are you hard? You're here. I want to help you. I will make your day so much more interesting. All I need is your attention. Someone liked your post. Did you know Jessica's on vacation? Here's a life hack theory. Here's some conspiracy theory. An influencer giving some fashion tips. A 9-year-old that died? Don't miss out on Black Friday. Take the test. What a day, huh? Staring at the ceiling is so boring. Someone just sent you a funny video.
Every day we're hitting endless content and inevitably feel bad about our lack of self-discipline. But
all right, I will stop it there because it goes on to some kind of social message. But anyway, did you catch where the Radiance Fields were used? Yeah, so every time she checks a message, right, it's a static setting, and then you kind of go around her, right, and that's a Radiance Field, right? So what they did was they put the actor in like different settings, probably took hundreds of pictures, and then recreated their environment using Radiance Fields, and they integrated this in the editing and production of this ad with a social message.
So we can do that with video only,
yes, but then the problem with video is that once you've taken a video, first of all, if it's a static scene, they have to be static. And second, once you've taken a certain path, you cannot change it post, right? Whereas if you have a Radiance Field, if you don't like a circular motion, so let's say you want like spiral motion, right? You can change it, right? So you have that degree of flexibility. And this is actually really important in movie making, right? So in movie making, the director might think, oh yeah, I think this camera angle is what I want, right? But then later when they're editing the movie, they realize that, oh, I should have gone the other way, right? So if you had a Radiance Field, you could totally do that, right? So that's at least the motivation behind this. Cool. All right. So, there's also commercial applications. And again, I took this example because the company that does this is local. So there's a company called Avatar, which is based out of Bengaluru, actually, if I understand correctly. And what they do is they build, if you go to buy a motorbike, or if you want to buy a treadmill in this case, right, and you want to know how this looks like, right, before you actually buy it, right? You can create these kinds of three-dimensional views. I'm sure you've seen this on many e-commerce websites. And some of these, I don't know about this one, but I know that companies similar to these have been using Radiance Field technology to create these kinds of 3D models, right, which they can then use to put it on their website so that consumers can look at how it actually looks like from all different angles before purchasing that, right? This is kind of also similar to the shoe example that we saw a couple of lectures ago. So it looks quite realistic, and you can actually get a feeling for how it looks like before you actually purchase the item, right? So this is like a major commercial application. All right, so with that, that brings us to the conclusion of this part. We've taken 5 stops so far in this lecture series, right? So we started off talking about the history. We started off trying to understand what radiance fields are. Then we talked about neural radiance fields. Then we talked about 3D Gaussian splatting applications. And hopefully today, I've given you a short glimpse at all the different cutting edge stuff that's happening that use radiance fields, that use priors to build radiance fields, that build, how people build camera systems to capture radiance fields, right? So hopefully that's given you kind of an overview of what's happening in the area. There's still a lot to do, both in terms of research as well as commercial industrial applications, right? So on the research front, how do we reduce the number of cameras that you need? How do we use generative video models to make these models better, lightweight? How do we build radiance fields in real time so that we can not only have static reconstruction, but also dynamic reconstructions, right? So those are all active topics of research that many groups in the world are working on, right? And again, on the application front, lots of people are now learning this technology and they're applying it in everyday settings, like the examples that we saw, right? Movie making, e-commerce, and so on, right? So there's still a lot to do. I'm really excited about what's going to happen in this field over the next few years. And hopefully I've given you a little bit of that excitement, and hopefully you've learned something in this course. And with that, I thank you for your attendance, and good luck. Yeah, I know we are out of time. If you have any questions, I'm up here for a bit.
So, I think the question is thank the speaker for giving 5 wonderful lectures. Okay. So, many of you would have benefited from these lectures. So, imagine again, okay? So, to give another series of lectures. Okay. So, thanks a lot.
Thank you, Professor Bhatt. Thank you. Oh, that's good. Thank you. Yeah, I should also thank all of you for the hospitality, and I think in 6 months' time the field would have changed quite a bit. So I'm happy to do another 5-part series. Yeah.